are going to be focusing on applications of the integral this unit. However, I guess it kind of is still applications of the integral. But most of what we're going to do in this unit is in Chapter 7 in the textbook. We're actually going to do one thing out of Chapter 6 that we sort of talked about before, but we're going to talk about it more formally, which is slope fields. Yay! But even in this section, it's not all about slope fields. All right, so before we actually talk about slope fields specifically, let's remind ourselves about solving differential equations. Really what this section will be, I think, is review of stuff that we touched on lightly before. So it shouldn't be brand new, but it's stuff we didn't really work on solid. But I'm just going to start with an example. Example. Determine whether the function is a solution to the differential equation and I'm going to give you a differential equation in a second, but before I do, does anybody remember what a differential equation is? I'll give you a hint. It's an equation. I know, I'm very helpful. When you hear the word differential, what's another word you might think of? Derivative. They're just equations with derivatives. That's all a differential equation is. So this particular one is y double prime minus y equals 0. So it doesn't have to be just the first derivative. As long as it has a derivative and it is an equation, it is a differential equation. So I'm going to give you 3 of them. We'll do the first one together so you get an idea of how to do it. But is y equal sine x a solution to the differential equation? Anybody have an idea how we would check? Rena. I missed the last part. Find the second derivative and that's exactly it. Since that differential equation has a second derivative in it, let's find the second derivative and let's plug it in, see if it makes it true. So what is the second derivative for sine x? Yes, negative sine x, because y prime is cosine and y double prime is negative sine x. And then we'll take that differential equation, y double prime minus y equals 0, and plug in. So y double prime is negative sine x. Y is just sine x. Does this equal 0? Ah, crap. Yeah, negative 2 sine x. That's not 0, so what do you think? Is y equals sine x a solution to the differential equation? That's right. Not a solution. So a very simple idea. So, any questions about that? Okay, so what I want you guys to do is check these two real quick. Look at y equal 4e to the negative x, and then look at y equals c e to the x. Give those a go real quick and we'll check them out. What did you think? Is B a solution? Excellent, it is. What about C? Excellent, it is. Now be careful with B. When you're doing the first derivative, it should have a negative on it. Because remember, chain rule, you'd have to multiply by the derivative of the exponent. But then y double prime just cancels out the negative. So, excellent. Any questions about that idea? So that's what it means to be a solution to a differential equation. And then we actually have two different types of solutions on here. So one solution is where you have that arbitrary constant still in there. So for C specifically, this is a general solution to the differential equation. And again, it's called a general solution because the arbitrary constant. Sorry, I have something in my eye. The arbitrary constant is, I don't know what the word is. We don't have a value for it. Probably should have started off with that. Is not solved for, I guess I'll say. But for B, anybody remember when we do figure out the value for C, what it's called? Like I said, we talked about it, but it's just so lightly. Yes, Rena. Well done, yes. This is called a particular solution. And a particular solution is going to have to give you some information to be able to solve for C. So, there's that. Any questions so far? Alrighty. So, here's another example. Let's find the general solution. Of x, y prime plus y equals 0. So there's different strategies for solving differential equations. This year we're only going to learn one, and it's a nice basic one, but I mean you can take a whole class in solving differential equations in college, but this year we're just learning about them. We're going to take it easy. We're going to do something called separation of variables. Not every differential equation can be solved using separation of variables. And separation of variables is exactly what it sounds like. We're going to separate the x's and the y's. We're going to put all the x's on one side. We're going to put all the y's on the other side. So, let's do it. We have x, y prime plus y equals 0. The first thing that we need to do is we'll have to rewrite y prime as dy dx. Because if we're going to separate our variables, we can see right there there's a y and an x in y prime. So we have to separate that. So anybody have an idea? What would be the next step to get the x's and y's separated? Or even if you don't have an idea. Anybody, like, is there anything that, oh, well, we could at least do this. Yeah, Yoche. That's an excellent idea. That is an excellent idea. Subtract y, divide by x. We definitely haven't separated them yet, but he's actually made it a little easier now. Y is a polynomial? Well, we don't know what y is. Could be a polynomial, could be exponential, I don't know. But we could multiply both sides by dx and then divide both sides by y. If I multiply both sides by dx, sorry, let me get rid of that dx. Multiply both sides by dx, so we're just left with dy on the left. Make this look better. So we get this. And then if I divide both sides by y, it's dy over y equals negative. And I'm going to go ahead and put the dx on top. You don't have to, but I'm gonna. So now we have the y's on one side and we have the x's on the other. Yay! Any questions? What we did, how we did it? How does this help? Because all I got to do now is take the integral of both sides. Yay! And then we can solve it. So what is the integral of dy over y? Meh. Oh, yeah. Gotta wake up. Ah! And what's the integral of negative dx over x? Yes. But we have a plus c. Actually, technically, what we have is we have plus c on the left. Oops. And we have plus c on the right. But then, remember, they're different constants. This is one arbitrary constant. That's another constant. Then we can combine them together for a brand new constant. So I could go then to natural log of y equals negative natural log of x plus a brand new constant. So typically, when you see people solving differential equations like this, they will not put the c on both sides because we're always just going to end up putting it on one side. So this step is typically not shown. But that's what's happening behind the scenes. And we typically put it on the side with the x because our goal is going to be to solve this guy for y. But any questions so far? Because now we have to solve for y. Oh my god, you guys look so excited. Yeah, we do. Now it seems like, dang, why not just drop the natural logs, right? But we can't. Dang it. What do we have to do? Any ideas? That negative is causing some problems. The negative and the c are causing a few problems. In general, when we have our variable trapped inside a log, what do we use to get the variable outside of log? We have to undo a log somehow. So in general, what undoes logs? It's a word that rhymes with mexponents. Exponents, yeah, very good. So we're going to use it, since this is base e, this is natural log, let's just raise each side to the power of e. So, anyway, let's do this. Not that. Let's do e to the natural log of the absolute value of y is equal to e to the negative natural log of x plus c3 po. That looks fun. The left-hand side is nice and easy, though. What does e to the power of the natural log of absolute value of y simplify to? Not just y. Yeah, we still have the absolute value. Can't forget it. Oh, but we're so close to getting the y by itself. Yes! Okay. But I need more room. Hang on one second. want to add a comment. Doop, doop, doop. Since now I got all this room, let's move this down here. Okay. That right-hand side. Can I just cancel out the e and the natural log right now? Why not? Exactly. Over here it was just natural log of something. But now we have a negative natural log of something plus this. Like there's, again, that negative and that c, they're causing some problems. So here's what we're going to do. We're going to do two things. First of all, we're going to use our properties of exponents. I'll make this bigger. We're going to use our properties of exponents to our advantage. And I'm going to make this e to the power of c3 times e. I'm also going to do something else. It would be e to the power of negative natural log of x. But let's also use the power rule to bring it as an exponent. So I'll let you double check and make sure you followed what I did there. Because this is a trick, this using the properties of exponents backwards from what we're used to. This is a trick we're going to use a lot in solving differential equations. So any questions why I was able to just pull this guy out in front? And e to some arbitrary constant is another arbitrary constant. So now I have the absolute value of y equals yet another arbitrary constant. And over here, now I do have just e to the natural log. And so I'm able to cancel out the e and the natural log, and we get Godzilla. X to the power of -1. We're almost there. We're almost there. This is very exciting. Very, very exciting. Any ideas now? Remember, we're trying to get the y by itself. Yes. Remove the absolute value. Oops, I forgot my C. And now technically I have the y by itself, but we're going to clean this thing up a little bit. So first of all, I could then pull this absolute value off, which would put a plus or minus on the y. But then I might as well just combine it with a plus or minus on this side. So, I don't need the absolute values anymore. And then for the grand finale, because we'll finally be done with this problem, plus or minus an arbitrary constant is an arbitrary constant. So now I'll drop off the subscript, because we have our final answer, and it is that. Yes? So, what I was kind of skipping through quickly, if I take off the absolute value to put the plus or minus on the y, but then I can multiply by plus or minus, like having a plus or minus here and a plus or minus there is the same thing as just having a plus or minus on one side of the equation. It's still plus or minus, so that's how I was able to do it. Any other questions? Now, one thing I will say, I think it's a good idea to get to at least think about these subscripts on the C's, because these are all different values of C. But you'll see, anyway, you'll often see that people leave off the subscripts when they're solving, so it makes it look like the same variable. But remember, they're really not. It's just arbitrary constants. So I will actually not take off points if you leave off all these subscripts that we have going on. But just know that they are different values throughout the problem. And try to at least think about it to yourself when the values actually change. Like, I was using C4 for quite a few steps, because this really is the same value of C. But this value of C is different than this value of C. So I changed the subscripts. But anyway, any questions? All right. So that's general solution because we haven't found C yet. And we can't find C. All this problem said was find the general solution of this. It hasn't even given us any information to find C. So all we can do is a general solution. But if I want to find a particular solution, need a new page. I'll do that. Okay, so part B to this problem. Oh well, this will be A. How about? Okay. Find the particular solution to y equals c x to the negative 1. And it'll say at given, I'll give different words here, but y of 1 equals 1. So it'll give you something to plug in and solve for c. So we literally do that. Let y equal 1. Let x equal 1. Oh my god. I keep saying it, but I'm not writing it. Anyway, can you guys look at this and see what c is? What times 1 over 1 is 1? 1. So our particular solution is just that. Let c equal 1. Any questions? All right, I'm going to go grab a little screenshot. Good. Let me put this back up here now. Sorry I get to cheat like this. I know it's harder when you're writing your own notes. But let's take a look at something, because this is going to lead into our slope fields then. When we've got general solutions, and this is an easy equation, like just y equals something over x, because that's what we've been dealing with, x to the negative 1 over x. Depending on the value of c, the graph of the equation is going to look different. Now in this particular case, if c is 1, then it's this hyperbola. It's got these two branches in the dark black. If c was 2, then it's these gray branches. If c is negative 1, then it would be the darker blue branches. If c is negative 2, then it's going to be the lighter blue branches. So depending on the value of c, your graph is going to look different. But so we can actually like graph all the general solutions on one thing. But then if we want to look at the particular solution at 1, 1, we can see that it's the black curve that went through the point 1, 1. So the black curve represents our particular solution. Any questions about that? So what often happens, the reason why we actually have these things called slope fields is sometimes you have equations that either you can't solve, differential equations that can't be solved, or maybe you don't actually have a differential equation. Instead, through observation or experimental data, you're able to determine the slope, the derivative, at different values. And that's what makes a slope field. So let's remind ourselves what slope fields look like. And this is going to be hard for you guys to draw. Do what you want on your notes. I'll be posting this. But again, I'm going to cheat here and grab this. But here's an example of 3 different slope fields. So it is a field of slopes. That's literally what a slope field is. So at this first one here, at the point, let's see here, that's 1, so this would be 1/2. So at the point 1/2, 1/2, we can see that the slope, the rate of change, is a little positive. Maybe we could try to calculate its exact value. But we can kind of see it's a little positive. It gets steeper, so the rate of change increases as we're moving to the right. Doesn't always happen. This one that looks like it is, but if you look at like graph C, sure, up here in quadrant 1, as we're moving to the right, the rate of change is getting steeper. But if we're down here in quadrant 4, moving to the right, we got negative rates of change. Something's decreasing there. So this represents a bunch of slope fields. So any questions what a slope field is? We don't do too much with slope fields in this class, so it's hard to appreciate how useful these things actually can be. Actually, back in my day when I did calculus, just a few years ago. Anyway, when I was a student, we didn't actually, slope fields weren't part of the curriculum because computers help us generate these slope fields much better than trying to do them by hand. And although, yes, we had computers back in my day, I'm not that old. We didn't have them in the classrooms. So anyway, but let's see if we can figure out which slope field goes with which differential equation. So I'll give you a second to look at that, try to figure out what strategy you might do. Talk with your neighbor a little bit. I'll give you a minute, but then we'll look at it. All right. Anybody have an idea, a strategy? And there's more than one way to figure these out. But Brina, what would you do? You could. So yeah, one thing you could do is actually solve. And number 2 definitely looks like an easy one to be able to solve, huh? Let's see actually what would happen. Now the only thing is we can't quite take the integral yet because have we separated our variables? Remember the dy dx. Y prime is dy dx. So you'd have to separate your variables and then integrate. What's the integral of dy? Good. Yes. And then what's the integral of x dx? But then plus c. So if you look at this one, I mean, no matter what the value of c is, x squared over 2 plus some constant, what's the general shape of this curve? Yeah, it's a parabola, right? And the x squared term is always going to be positive. So we know it's always going to be a parabola that opens up. So looking at A, B, and C, can you see which one represents just a bunch of parabolas? I know we can't do A, B, and C on our fingers, but 1, 2, or 3 for A, B, C. Which one do you think looks like a bunch of parabolas? Some people are still showing me letters. I love it. Yeah. A is actually it. That's good. Now, I only saw a few people showing me fingers, but the way you look at it, and here's another strategy. Here's a strategy for finding a particular solution on it. If we just picked a value, like a point x, y, let's see what would happen if we're at this whatever this point is. Actually, I'm just going to move this down a little bit so I can point. Wrong thing. So if we look at this guy right here, just starting somewhere, pick one of the slopes at random. Imagine it's like a stream and these lines represent the flow of the water in it. If you were to follow the flow of the water, starting here, it looks like it's going to take you in a parabola shape. And these are just a bunch of parabolas that are shifted up and down from each other because that's the plus c that we have. So that's actually a really good way of doing it. If you can easily solve it, yeah, you can totally do that. So now we know this guy is A. But you don't have to solve them. The nice thing is you don't actually have to solve each one of these equations to do it. Because another way you can do it, notice these are all solved for y prime. They're all solved for the slope. So let's just look at this one since we already know this one now. The slope is equal to the x-coordinate. Whatever the x-coordinate, that's the slope. So if we take a look at right here where x is 1, look at all of these slopes lined up with x equals 1. See how they all have the same slope, and it does kind of look like they might have a slope of 1. And as we get our x values get bigger, the slopes are getting steeper. Right here where x is 0, all the slopes are 0. And then over here where x is negative, all these slopes are negative. That's another way to be able to match it. So if we use that strategy, look at number 3. The slope is the y-coordinate. So which one looks like the y-coordinate? Is it B or C? Yeah, I'm seeing a bunch of C's now. So if we look at C, where y is 1, all these slopes look like they could be 1. All of these slopes on the x-axis, where y is 0, have a slope of 0. All these slopes below the x-axis are negative, where the y-coordinate is negative. So this is C. Process of elimination, then. We know that equation 1 is B. It gets a little trickier here. The slope is the x plus the y-coordinate. But let's just look, if x is 0, then the slope is the y-coordinate. When x is 0, when x is 0, I just lost it. Okay, it's right here. Wait a minute. Why am I being thrown off? X is 0. When I'm having a brain fart, and this is very embarrassing. When x is 0, you're on the x or the y-axis. You're on the y-axis. Why is that so hard? Anyway, when x is 0, you're on the y-axis. I'm looking at the wrong graph. That's fine. So here we go. Now when your x is 0, you're on the y-axis. Looking at graph B, we can see that these are negative, these are positive. And then likewise, when y is 0, the slope is the x-coordinate. You can see it seems to be matching the x-coordinate. So you kind of look at them like that. Any questions there? All right. So 2 other little things, and then we'll be done with the notes. Let's make our own slope field. Now, we're not going to go through a whole lot. We're not going to make one, because, I mean, oh my God. How many different values? 1, 2, 3, 4, 5, 6. 81 different slopes are on each one of these. We're not going to do that. We're going to make a very simple slope field. I haven't seen them do it in a while, but I have seen them on the FRQs. I think it's just happened like once or twice where they actually ask you on the AP exam to make a slope field. Most of the time it's just using a slope field. But let's just see how we do it. Sketch a slope field. For y prime equals 2x plus y. And we're going to go from -1 to 1 on the x-axis and -1 to 1 on the y-axis. We're going to make it very simple. And there's actually some different strategies depending on the equation that you can do, but I'm going to give you one strategy that works every time. It is a little tedious, but this will be the strategy that can work every time. I am going to actually, we're just going from -1 to 1. I'm going to space this out though. That's 1. You basically just pick points and plug them in. Let's just do 9 points. We're going to pick these 9 points. We're going to keep everything whole numbers. This is kind of the brute force method. You literally plug in. Yes, Rena. Oh, negative. Yeah, thanks. All right, so if we're going to do y prime equals 2x plus 1, it's all based on the x coordinate. That's good news. So when x is -1, what is 2 times -1 plus 1? -1. So let's make a little dashed line that has a slope of -1. And basically what I'm doing, I'm like imagining if I go over 1, down 1, I'm imagining, that triangle to get my slope. And then when x is 0, what's 2 times 0 plus 1? 1. So now I'm going to make a little dashed line with +1. And then finally, right here, where x is 1, what's 2 times 1 plus 1? Yeah, this is where it gets hard, because how do you like make one that's exactly? Anyway, I do imagine like over 1 up 3, so it's got to go through that. So I'm kind of picturing that in my head. I'm not going to like take a protractor out and measure, does this exactly have a slope of 3? But it should at least look steeper than your slope of 1. That I will look for. There you go. There's your first slope field. How do you feel? Feel great? Okay. The last thing is going to be something also that you will have trouble drawing, but it's a very simple idea. Does anybody need this though? Because I'm going to scroll off. We're going to look at a bigger slope field. All right. So this guy right here, make it bigger so we can see it. So one of the things that we use slope fields for, when we can't actually solve the differential equation, I mean, this one we might be able to solve for, actually we could, but let's say you have something that's too complicated and you can't solve for it, or you don't actually have a differential equation, you just have a slope field because you were able to measure all these rates of change, but you still want a graph to represent the function. Then you start at whatever point you want, whatever point applies to your particular situation. I need to move this down. So in this case, let's say that we're starting with this initial condition, and then you basically follow the flow of the lines. Starting here, the slopes are negative, but they're getting less steep, and then finally it looks like they change to a positive slope. So it looks like it's making that shape. And then you can use that to then model your whatever situation it is. And that's one of the uses for a slope field. When you take Calc BC, you'll learn about some other things too. Any questions? All right, that's it. I hope you guys have a wonderful week off. Yeah. Lucky ducks.